Hello everyone, this is lecture 5 for the spell theory of relativity. In the last lecture, we studied about the momentum and the energy and what it take place or what it's mean in the relativity and how we define the terms of energy and momentum in the relativistic case. So, we were discussing some examples. So, let's move forward with some more examples. There is this one. The energy of a very relativistic particle is equal to this, where m is rest mass, p is its momentum, and c is the speed of light in vacuum. The ratio of Vg divided by Vp of the group Vg of a quantum wave packet describing this particle to the phase velocity Vp is. So here Vg and Vp are the group velocity and the phase velocity of the wave packet. We have to find the expression for them. Okay, so options are given A, B, C, D. So how are we gonna solve them? So from the quantum mechanics, we know that what's the formula for the phase velocity for a wave packet, that is omega by k. If you multiply and divide by h cut, then we will get h cut omega is energy, obviously the h by 2 pi and 2 pi by t, that will give us the energy. And for the k, h cut k will give us the momentum of the wave packet. And if we talk about the group velocity of the wave packet, then that will be d omega by dk, and it is nothing but de by dp. Okay, so we need to find this expression to calculate the vp by vg ratio. So how are we going to find this? We know the expression for the energy is E square equal to P square C square M square C4. So from here, just take a derivation, differentiation of energy with respect to momentum. We will get 2E dE by dP. That will give us 2P C square plus, that is constant term, that is 0. From here, dE by dP, we will get PC square divided by E, which is Vg. Now we know what is Vp and we know what is Vg, so just divide them and the ratio will be this. So this is option C. Let's move to the next. So there is one more question. A particle with rest mass capital M is at rest and decays into two particles of equal rest masses 3 by 10 m, which move along the z-axis. Their velocities are given by. So we have to find the velocity, okay, of the particles which will decay from the single mass m, which is at rest initially. So let's say this is that mass m which is at rest. So its initial momentum will be 0, and when it decays into two particles, then the sum of those momentum will also be 0 because, from the conservation of momentum law. So p initial 0, pf should be 0, and they will move in opposite direction with equal momentum. That will give us resultant 0. But we know that energy will remain constant, the initial energy and the final energy. So we'll use that thing. So if they have the same mass, so velocity will be the same but in opposite direction. Okay, so let's say v1 will be vz cap, and v2 is minus vz cap. Okay, so and it is given, it is not given, we have to calculate this. Okay, that's what the question, we need to find the velocity. So initial energy of this mass is mc square, capital MC square, that is the total energy, will be equal to the sum of the energy of these. Okay, so energy of these will be, what will be the energy? So the mass is 3 by 10 m, and speed is v, we need to calculate. So total energy will be mc square divided by root 1 minus v square by c square. So from this expression, the m will be cancelled out, and when we find the v, that will give it will give us v equal to 0.8 c. 0.8 c, that will be for v1 it is plus, and it is minus for the v2 in the z cap direction. Okay, the next question is the k meson with rest mass energy of 494 mega electron volt at rest decays into a muon with rest mass 106 mega electron volt. So it is rest mass energy actually, but it was written as mass in question. But from the units mega electron volt, we can see that it is energy. And a neutrino, the energy of neutrino which can be massless is approximately. So k meson divides into two. One is our neutrino and the second one is the muon. So we have to find the energy for neutrino. okay, because the energy for muon is given, that is 106, but this is rest mass energy. Okay, just remember this point. So we can see from this expression that k decays into muon and the neutrino. So initial momentum is 0, so some of these momentum will also be 0, and energy is given. The mkc square is 494 mega electron volt for the k meson, and for r muon, c square, this is given 106 mega electron volt. And for neutrino, these are the rest mass energy actually. So for neutrino this will be 0, because rest mass of neutrino is 0, it is massless. And we know that if final momentum have to be 0, then both particles should have the equal and opposite momentums after the decay. Okay, so this will be 0, so both momentum will be equal but opposite in sign, so magnitude will be same. We will take it at p, take it as p. Okay, so energy of total energy of k meson will be mkc square. Okay, and for the muon, if we wanna, this is the energy expression we know for muon. When we find the energy, that will give us just the rest mass of muon here. P is the momentum, p square c square, this is the energy for muon. And for the neutrino, we know that rest mass is 0, so it will give us p square c square will give us pc. So e neutrino will be pc. This is the energy for muon, this is for neutrino, this is for k meson, so this will be equal to sum of these. So write it like that. This is this. Now from here we will find that pc will be here minus, and square of this will give us this expression. And after cancelling these out, we need to find pc actually now, because the question was energy of neutrino. For neutrino total energy was pc. So for pc, if we find we want to find the pc from here, then it will give us expression as E nu equal to this mkc square whole square. This will be the expression for. Now put the values and you will get the answer. So move to the next question. A particle of rest mass capital M is moving along the plus positive x direction. A mass M is moving to the positive x direction. It decays into two photons, gamma 1 and gamma 2. So two photons. As shown in the figure, the energy of gamma 1 is 1 giga electron volt. So energy of gamma 1 is given, that is 1 giga electron volt. And energy of gamma 2 is 0.82 giga electron volt. So energies of both of the photons is given. We need to find the value of M in units of giga electron volt divided by c square. We need to find this mass M. Okay, so what we will do here, we will use the conservation of momentum law, that this is, if momentum is p, then this will linearly, the momentum linear momentum will remain constant, so it is p here. And if we take the x component of gamma 1 and gamma 2, then that will be equal to, that sum will be equal to p, and the y component will be cancelled out. So this will be equal to this, so just solve it in that way. Now the gamma 1 and gamma 2, the total energy will be 1.82 electron volt. We know the energies now, that's why we can calculate the sum. So initial energy will be equal to final energy. So 1.82 electron volt will be equal to what? P square c square plus m square c4. This is the total energy for m, the initial particle which decays into the photon. So that is the energy for that. From here we can find the expressions. We know that what is p? What is p? As I just told you, that p will be the sum of these two momentums in the x direction. So if it is p1, then p1 cos 45, p2 cos 60, this will be sum will equal to p. And we know for photons, that is massless, for them the p1 will be given as e1 by c and p2 will be given as e2 by c, because the energy for a photon is equal to pc. Okay, so p will be equal to p1 cos 45, p2 cos 60, and just use these energies. E1 is given in the question, E2 is given in the question, so P1 and P2 can be calculated. From here we will find the total momentum as 1.11 giga electron volt divided by C. Now just put these in this expression. We have the value P and we know C. We don't need to put the values for C here. Actually, just calculate the expression for m square. That will give us the mass in terms of giga electron by c square. Okay, find the value of m, so that will be this. Okay, that is m equal to. Now there is one more term, that is a relativistic form of Newton's second law of motion is. So in relativistic case, how we define the Newton's second law? So we know the second law of momentum is that force is equal to rate of change of momentum. So F equal to d by dt, and P is mv, and that mass is relativistic, so we will use m naught by root 1 minus v square by c square, where m naught is the rest mass v. From here we know that c square come here and the c will come out, and m naught is constant, so m naught c will be out from the denominator, c will go up and constant, that then outside m naught c will be out. Now inside of d by dt we have this expression. Just take it differentiation using the formula of dividing, that the square of the denominator, then put it as it is, the derivation of, sorry, differentiation of first, the upper one, minus the differentiation of the denominator and multiply by numerator. So use that formula and you will get this expression. From here we will see that when this is multiplied here, the c square minus v square d by dt will be taken common, 2 will cancel out, and it will came just like this. This will came this, and c square minus v square, this will cancel out, c square by this, and from here this will turn into c cube d by d2, and this is 1 plus 1 by 2, that will give us 3 by 2. So this will be the expression for the Newton's second law in the relativistic case. Now there is one more question, that is, consider the decay process. It is given that the tau is divided into pi and neutrino. Okay, so in the rest frame of tau, the masses of tau, pi and neutrino are these. We know that neutrino's mass is 0. Okay, so we take it as 0 here. We have to find the energy of pi negative, that is meson actually. So these are the options. So how are we going to find this? So there is a standard formula to calculate these types of problems, that is just to put the sum of energies equal to initial and final energy equal. So E pi plus E neutrino equal to E tau, and E tau that will be given as m tau c square. Okay, if rest mass is m tau, then for tau which is at rest, so total energy will be m tau c square. From here we know that for E pi, that will be energy is given by this expression. For neutrino, where rest mass is 0, given by this expression. And now put this expression, means just we divided from this equation is divided. Momentum we take the same in both the cases, in the pi and neutrino. Why? Because when this decays into two particles, that will move in the that will have the same momentum both in the opposite direction. That's how they will give the net momentum 0. Okay, that's why we take the momentum same, the magnitude is same actually, that is p. Now minus this from this, that will give us, this will cancel out, m pi square c4. From here just use a plus b, a minus b. From here e pi minus ev, we will get this. Now we have two equations, x plus y equal to this, x minus y equal to this. From here we can calculate e pi. Just add these equations, 2 e pi will begin this, and e pi will be this. This is the formula for e pi, and that was the question actually, the energy of pi is. So that's how you can calculate this. If we add one more question in this question, that find the velocity of pi. We have energy, now we can find the velocity too. How? Total energy for pi will be, this is rest mass c square divided by 1 minus, if it is moving with v speed, then 1 minus v square by c square. Then put the value of e pi from the back expression, that will give us this expression after solving that. Now the important topic of today is the relativistic Doppler effect in light. Now, as you already studied what is Doppler effect, That is just apparent change in the frequency and the real frequency we studied in the school level, and that was just for the normal cases on the earth. Now we're gonna study the Doppler effect in the relativistic case, when there is speed of light involved and the relativity is involved. Okay, so it is not that hard, it is just very easy. So let's say there is one source. Okay, this is source, and this is moving with v speed in this direction. Okay, in this direction, and at t1 time it emits a radiation. Okay, it emits a radiation that is in this direction, and there is this receiver on earth. This is receiver, and if it emitted at t1, these all times are we are measuring in the earth frame. So at t1 it releases the radiation, and that radiation will be observed here. Means if there is one photon is released and it came here, it will be received at t1 r time, and after t2 minus t1 time, at t2 time it emits, when it came here it emits one more photon. Okay, and that will be received on the receiver at t2r time. Okay, so first emission here, second emission here, and it is at t2r, it is at t1r. Okay, so hope you get it, that what we are seeing here, there are two radiation observed at t1r t2r, and emitted at t1 and t2. So if this length is L, take it just like parallel to this. Okay, it was just wrong display. It was L and it is also L. Then this extra distance will be, if delta t is t2 minus t1, difference between these times is delta t, then v delta t will be this distance, and this will be v delta t cos theta. Okay, so this whole length will be L plus v delta t cos theta, and this is L. Okay, so we take delta t as t2 minus t1. From here, if we see that radiation is emitted at t2 and reaches here at t2r, then this time will be the time covered by a photon, okay, to traveling this distance. So time will be distance upon speed, that will be L by c. So if it is was t2, then t2r will be t2 plus L by c, and t1r will be t1 plus L plus v delta t cos theta divided by c. Okay, from here we get these times. Now difference between these times will be t2 minus t1, and this will minus this. We'll get t2 minus t1 v delta t cos theta divided by c. Now we represent this time as delta tr, and this is, we know, delta t 1 minus v by c cos theta. So it is easy, just maths. From here we can find the frequency. Okay, so we see that in delta tr time we received one signal. There is this and this, so in delta tr we will receive one signal. Okay, and if we know that in delta tr time we receive one signal, then in 1 second how much signal we will receive? 1 by delta tr. So that will give us the frequency observed here by this observer on the earth. So frequency will be, frequency of light as observed by the observer detector will be 1 by delta tr. That will be the frequency. So we know that this is nu. So now we have to calculate how much this will be, the nu will be. So this is apparent frequency detected by the observer. Now the what is the real frequency? So we know that the real frequency will not be observed by this observer. The actual frequency is observed by the someone who is at this object here, this source, who is on the source, because that person will measure the actual time difference between these signal passed. Okay, this person who is on the source, sitting on the source, will measure the actual time between this. Okay, so we will call this actual time as delta t naught. From time dilation we know that this time will be in if observer is measuring delta t time and actual time is delta t naught, then delta t will be delta t naught by 1 minus v square by c square, and v is the speed at which the source is moving. Okay, so from here we can calculate the delta t naught, and 1 upon delta t naught will be the real frequency. 1 by delta t naught will be real frequency, so mu naught will be 1 by delta t naught. Okay, and from here we can just use this expression, that delta t equal to this, put it here, put it here, and that will give us, this will be 1 by mu naught, and in the denominator we will get this situation like this, and 1 by delta tr will convert it to 1 by mu, sorry, delta tr will be converted to 1 by mu. Mu is the apparent frequency, mu naught is the actual frequency, and from here we will get an expression for mu, that will be mu is equal to mu naught root 1 minus v square by c square 1 minus v by c cos theta. So this expression will give you all the answers. Just this only formula can solve any type of relativistic Doppler effect questions, any type. So just let's see some cases. When source is moving towards the observer, then this theta will be, what is the theta? Theta is the angle between the observer and the source. Okay, and the source velocity, the direction of the velocity. So that was v here, and this is this. So this was the theta. Here the direction of v is also here, and this is also, this theta will be 0. So just put cos 0 equal to 1 and solve it like that. Cos 0 will be 1. From here we will see that 1 minus v by c, it will turn into 1 minus v by c, 1 plus v by c. So 1 minus v by c will cancel out, in the down denominator we will get root 1 minus v by c, and overall will give this expression. Okay, so from here we can see that what is this apparent frequency? This will be greater than 1, this overall will be greater than 1, so mu will be greater than mu naught. Okay, so it means that when source is moving towards the observer, then the observer will measure a greater frequency than the actual frequency. Okay, and it's just in the opposite cases for the wavelength. If more frequency is measured, then less wavelength will be measured. Okay, so it means that when light source is moving towards observer, then apparent frequency will be greater, that is frequency is shifted towards the blue. If it is visible light, then we can say that it will go, frequency will be increased. So in the spectrum we see that for the blue part, blue color region, we have the higher frequency. So that's why, due to this reason, this effect is called the blue shift, when the apparent frequency is more than the real frequency. In case 2, the source is moving in the opposite direction from the observer, so angle will be 180 degree, and this will turn this into minus 1, then 1 plus v by c, and it will be just opposite, 1 plus 1 by c, then the plus factor will be cancelled out, and in the numerator we will get 1 minus v by c, and so this expression will give us this, mu is equal to mu naught this. Now here from this we know that this is less than 1, so the actual frequency, sorry, apparent frequency will be less than the actual frequency, and just opposite, wavelength will be greater than the actual wavelength. So we know that in spectrum the red color has the more wavelength, so this will call the red shift. And these are the longitudinal Doppler effect also. Okay, longitudinal, why is longitudinal? Because the angle is in parallel direction to the observer. Now there is one more case, that is transverse Doppler effect, that came into the picture when our source is moving in perpendicular direction with the line which is joining to the source and the receiver. When source is moving perpendicular to line joining source to observer, this, and source is moving at 90 degree with it, then we will call it the transverse Doppler effect. And from the formula we know that it will turn out to be 0. It will give us mu equal to mu naught root 1 minus v square by c square, and this is less than 1, so mu will be less than mu naught, and lambda will be lambda greater than lambda naught. So okay, thank you, we will end here today's lecture. Tomorrow we're going to discuss some transformation of momentum and energy. Okay, then we will go into the 4-dimensional space, the Minkowski space, and the rotational matrix, and that will be the last topics we're going to discuss, and some questions. So it will take two, 3 or 4 lectures more. Okay, so till then, take care, bye bye.